Hi everybody, I'll just adjust my webcam so it can actually be seen. Hopefully you can all hear me and see me relatively well. Sing out on the chat if you can't. Obviously that's a bit of a misnomer, but hopefully you can all hear me. Welcome, I suppose, to the first DBA office hours that we're holding. You've probably seen some of the other office hours sessions that we've been already presented in the last few weeks. We're pretty excited about this initiative because it really lets us get out and actually see the community, even though we can't actually travel to your workplace. So in terms of time zones, if you're joining us from Europe, thanks for joining us for breakfast. If you're in Asia or India, thanks for joining us for lunch. And if you're in the eastern states of Australia, well, hopefully this will help you with your dinner. And for anyone joining us from the US, well, hopefully this session might help you get to sleep because it's very late there. It's absolutely cooking here in Perth today. It's nearly 40 degrees. So if you see me start to melt, don't panic. It's just because of the heat. Just a couple of things on office hours, just to help explain things, because I've had a few questions about this in terms of the sign-up process. The way office hours works is you're actually signing up for the type of office hours. So if you've signed up on this session using the register button and you've signed up for the DBA office hours, then every month when myself or someone else holds the DBA office hours, you're automatically registered for that. So you'll get an email reminder, as you probably saw if you've registered for this one. Obviously, you can just come back at any time and hit join, and that's no problems. But yeah, so you actually don't sign up for an individual session. You actually sign up for the DBA office hours program, so to speak. So every month you'll get a reminder if you've registered. Same with all the other office hours ones as well. If you sign up for Java or JSON or anything of those things, then you'll get an email effectively every single month. A couple of ground rules before we get started, and this is really a simple fact. Please don't ask me about the particular SR you've got. I can't see it. I don't have access to all the SRs. I just have access to SRs that I log in. And yes, as an Oracle employee, I log SRs as well. And that's what we do. The other thing, so I just got a message on my screen saying some people need to upgrade their Zoom. Well, hopefully it's not whoever's watching. If you want to ask questions throughout the session, please ask them via the chat. You can send them to everyone, which means everyone will see them, or you can send them to me privately. It doesn't really matter. If you signed up for office hours, you may have seen that there's actually an ability to log questions even in advance of the session. And we actually had a number of come in, so we'll deal with them first once we get onto the topic, just to give them the right of reply. But obviously you can fire your chat questions away as we go. And the only other thing is, please don't ask me about licensing, especially because we're talking about partitioning today, which is obviously a separately licensed option. But yeah, so licensing is the decisions about licensing inside Oracle are made like way up here at the very highest levels. And I'm about here, in fact, probably off the screen, like right down the bottom. Okay, so I don't get to make any calls on licensing. Obviously, in terms of the cost of Oracle partitioning, the objective is if you're using it to get the absolute best value out of it, so you get value for money. So we're talking about partitioning today. So what my intention is with the DBA office hours is that what we'll do is we'll have a particular topic that we'll try to talk about each month. I had a number of questions come in just from user groups and various conferences in the last 12 months about partitioning. So I thought that would be a good way to start. So we'll talk about partitioning today. If we run out of questions or you lose interest, that's fine. We can move on to other DBA topics. That's no problems at all. But we'll cover the questions off, and as I said, you can fire your questions on. And obviously, we can run for the whole hour, or we can simply run until we run out of interest or time or questions. These are meant to be fairly ad hoc, nice and flexible, and easy to get going. So let me switch to one of my slides. Let's have a look. Okay, I'll just share this. So the first one that came in is, can I use partitions on standard edition? Well, I suppose we'll cover that off first in the sense that not only can you not use partitioning on standard edition, you can't even use partitioning on enterprise edition. It's actually a separately licensed option. So if you're paying for an enterprise edition license, some people run under the misconception that you can use anything and everything under the Oracle database. There's actually a licensing guide in the standard documentation which tell you what you can and can't use. I wish partitioning was included in all versions, simply because the reality is the world we live in, databases are getting bigger and bigger and bigger. And so partitioning is probably the most important facility you have to actually manage large data sets. So I can't stress enough. I think it's worth the money, but obviously I don't hold the purse strings, so you have to make that decision yourself. So the question is, can I use partitioning on standard edition? Well, no, but what you can do is, if we think about the history of Oracle partitioning came in back in Oracle 8.0. That was when the first partitioning options came available. Before that, people still had these problems. Even back in Oracle 7 days, people had databases that were getting just too big. So we came up with a system called partition views. And the way partition views work is you could create multiple tables, put a standard database view over the top of them, and treat it as if each of those tables were like separate partitions. It's not as clean or as neat as the partitioning option, but it was the way people did it back in Oracle 7. Now that functionality has not changed. It's never been taken away, so it's still there. So in fact, let me share my screen. I'll change this and share my SQL Plus window. And let's have a look at what we can do with partition views. So these are some scripts I built up in preparation for this session. So hopefully you can all read that. Hopefully the font's big enough. So what I've done, I've created 3 tables here, T1, T2, and T3. They're not partitioned, obviously. They're just 3 totally separate tables. Each one is a copy of DBA object, or all objects. So there's maybe 70 or so thousand records in there. I've added a column as a prefix to each of them, which is going to become our partitioning key in this case. So I've got 3 regions: Europe, Americas, Oceania. If anyone's joining us from Africa or Asia, my apologies. I just didn't want to chew up too much of the screen space. So we have 3 tables here, but we'd like to view them as a single entity. If you've used partitioning, you're probably familiar with list partitioning. So we might want to present these 3 tables as if it was a single table, a list partition on that region column. How can I do this in standard edition if I don't have a partitioning license? So the first thing we do is, let's add some constraints to each table to make sure we can't put data from a different logical partition into those tables. So T1 is only allowed to contain information from Europe. T2 is only allowed to contain region of Americas, and T3 likewise can only contain Oceania. So those check constraints are important because they're going to be useful to give the optimizer some information. Now I'm going to create what we used to call, way back in Oracle 7, what we call a partitioned view or partitioning view. And it's a fairly simple definition. It's simply, I've got a logical object called T now, a view called T, and it is the union all of all those 3 objects, T1, T2, and T3. It has to be union all. In fact, it's best to be union all because by definition, no row can exist in more than one of those tables because of that check constraint. I can't possibly put the same row in any of the 3. Union all is important because a normal union inside Oracle would do a massive sort if I was going to query those tables to remove duplicates, and we don't want that. So having defined that structure, you can view T as our partitioned table, and I use that term loosely because it's obviously a view, and T1, T2, and T3 are our logical list partitions, where each partition is based on region. So let's now do a query. I've turned auto trace on to trace only explain. So that's only going to do an execution plan. We're not actually going to run it. And I'm going to do an execution plan on select star from T where region equals Europe. Now, at first glance, you might be thinking, well, I haven't really gained much here. I can see there that it's accessing T1, T2, and T3. It's going to scan all 3 tables. That's no good because partitioning, one of the features of partitioning is that it should be able to do partition elimination. So let's look a bit closer here. You can see that what we've got is we've got a union all, and then we have table access full on T1, and that's the region where your region equals Europe, and we're expecting to get 73,000 rows, which is the whole table. That much makes sense. When I look at T2, it's doing table access full and expecting to only get 1 row, or effectively near to 0. Now, not only is it expected to get minimal rows, which is correct, the key thing is this line before it, filter, line 4. If we drop down to the predicate information, we can see the filter is actually null is not null. That's a line that will never, ever be true. So everything under 4, which is these 2 lines here, they're never going to get run. It's actually never going to touch table T2. And similarly, if we look at 6 and 7, we have a similar filter, null is not null. It's never going to touch table T3 either. So the classical definition of partition elimination still works with this old Oracle 7 technology, which is partition views. If I do select star from T, where region equals 0, I'm only going to access table T1. So if you've only got standard edition, you can get close to partitioning, or if you haven't got a partitioning license, using partition views. Came in Oracle 7 and is still there. The reason I say close to partitioning is obviously it's not a complete implementation. For example, if I try to do DML against that view, then I can't do it. I can't do DML against a view. It's a union or view. Now you might be thinking, oh, I could use maybe an instead of trigger, and that's possible, but be aware that DML on a view that contains an instead of trigger is not the same as normal DML. There are certain things you simply can't do with a DML trigger that you would prefer to do with normal DML. But there's not it. So to answer that first question, yes, it is possible to do partitioning in some way, shape, or form on standard edition if you haven't got the license. Okay, let's move on to the next question. And that is, when would I have a global partitioned index? Okay, so let's do a quick review of indexing on partitioned tables first. Okay, see the screen. Okay, so let's do a quick review on indexing on partition tables. I've got a table here called sales. And effectively, it's got 4 partitions, 2009, 2010, 11, and 12. And I create an index on that sales table, just a conventional index. The obvious question is, how does Oracle treat that when you create an index on a table which is actually made up of 4 physical segments? This is what actually happens. We get a single index structure that spans the entire partition table. This is what we call a global index, right? And the term global stands for a single index spans all the different partitions. It's a really big index, as you can imagine. Generally, we have partition tables if tables are getting really, really big. But what I mean by big is, because that single index doesn't just have to reference rows, it has to reference objects as well. It needs to know not just the row ID, it needs to know the object in which that row ID, that particular row will exist. So it uses a thing called an extended row ID. It's actually a 10-byte object in the index, as opposed to a normal row ID, which would only be 6 bytes. And one of the problems with global indexes is what we have this thing called ILM issues. And that is, one of the benefits of having partitions is we can obviously do things like partition maintenance. So I might choose to, for example, to drop off all the stuff from 2009. If I've got a single index that spans that entire table, then it actually breaks the whole index in most versions of Oracle. That index no longer becomes accessible. If it's been used for, say, a primary key, then your table could be really broken. But what normally happens is, for most indexes, it simply becomes not eligible for use by the optimizer. And that's because there's an initialization parameter called skip unusable indexes. And it simply says, don't use that, don't consider that index as being a candidate for use, because we can no longer access it. And this is, it's sort of in script form, this is actually what you would see. I create an index, it's valid. I can use that index table access by global index row ID. I then drop a partition and it becomes unusable. If I repeat the same query, it simply says table access full. I didn't get an error, it simply said I can't use that index anymore. So that's a global index. And that's because, as I said before, of this parameter skip unusable indexes. If you set that to false, then once an index becomes unusable and you try to use it, you actually get an error. And that was actually the default behavior back in Oracle 9 and 4. So you can choose to keep the index valid. And the way of doing that is, when you actually drop the index, you say update indexes. And so what happens is, rather than actually just marking that whole index as being unusable, effectively what it does is do what you would do manually. Effectively go delete all the entries from the index, like a big delete command, and then remove the table partition, leaving the index sort of in that state like that. So the index is still valid, but there's a very large cost to doing so in doing that. And so that's the thing with the global indices. It's much better in 12c, but I saw that we actually had a question on that, so we'll cover that one later on. In 12c, we'll talk about that. So then we had local indexes. So just in terms of review again, a local index is an individual index structure on each particular partition. So to return to our question, and that is, why would we have a global partitioned index? And that is an index which is actually partitioned, but not necessarily on the same partitioning scheme as the table. Now, there's pretty rare nowadays, because you get the drawbacks of global partition indexes, which is they need to be rebuilt if you do partition maintenance, and you don't get all the advantages of local indexes, even though they're partitioned. So the question is, why would you have a global partition index? Probably the most common example I see of that is what we call a hash partition global index, and that is for avoiding contention. So let me set the scene here. If I have a table, which is probably one of the most common things we have, I have a sequence to generate the primary key. And that sequence is simply every time I insert a new row, I do sequence.nextVal. So the primary key is an integer that continues to go up and up and up. Now, why do tables get large? Well, if they're rapidly inserted into, that's obviously one way they get large if it's not a batch kind of process. So there's a very good chance on big partition tables that I've got a lot of insertions going on all at once, all getting that sequence.nextVal. So even though an index is a nice balanced tree structure, every single insert is trying to add a row to the very right-hand side of the index, the very leading leaf blocks. So we might get contention on that very right-hand side row. Now, you'll see sometimes people say, oh, my index might get unbalanced. And people think that indexes sort of start as a trend and drift off to one side. That's not true. The index always stays balanced, but everyone's working along one little end of the index, really belting away at that. There's a problem with that, and you get contention, and that slows down the rate of inserts you can do. One of the ways of avoiding that for that particular primary key index is what we call a global range partition by, a global partition by hash index. What that actually does is splits that single primary key index into multiple partitioned indexes. So what happens now is I actually have 4 or 8 or 16 partitions comprising that single index. Every time I insert a new row getting sequence.nextVal, what's going to happen is I'm probably going to go to one of those 16 partitions. I've spread the load over now 16 of those individual index partitions, as opposed to all competing for one physical segment. So using global hash by is a really cool technique for primary key indexes that have those leading edge sequence values. Really good way of avoiding contention. That's probably the only real use case I've seen for global partitioned indexes that aren't locally partitioned. Okay, let's flip back to slideshow. What's the next one? How do I quickly load a reference partition setup? Okay, let's have a quick review first of reference partitions. Because I can't get my other camera working, I'll have to show you some slides again. Once we find them. Reference partitions. So reference partitions handles the situation of when you've got two tables linked in a standard parent and child foreign key relationship, and I want to partition the parent, and as a result, I might want to partition the child along the same lines as the parent. Now, before reference partitioning came along, the way we did that was we would actually individually partition the two tables, and as a result, the partitioning key for the parent, which might be, say, a date column, would have to be copied down into the child, even though the child didn't really need it. So here we have an example on screen. I've got a table called parent, and I'm partitioning it by that date column, DTE. and it's broken up into monthly partitions. I've also got a primary key, PK, and that's just a single global index sitting across the entire table. It's a normal primary key. Partition by reference says, well, I want to partition my child table by that same date column. So I want to break my child table up into monthly chunks, just like the parent table. But I don't want to have to copy that date column down to the child because it's not really needed to be there. And the way I can do it is using a on-delete cascade foreign key, and then the name of that constraint lets me nominate partition by reference on that constraint. So I'm saying, as I come to insert a row into the child table, to work out what partition to put it into the child table, I'll grab that foreign key, go to a lookup on the parent table, find out what partition it goes into, and use that to create a child partition or use that for my child partition. So in that way, every row that goes to the parent, its children rows will be into a logically equivalent partition in the child. And here's an example. I've put 100 rows for 100 different dates into my parent table. That creates me probably 3 months worth of partitions. Then I insert the same 100 rows into my child table. And we can actually see that if I gather stats on the child, it actually created partitions based on the child table and actually put some rows into partitions here, each one for a particular month, even though the child table has no reference to an actual date column. It went and looked up the parent table to actually work out what date partition it should go into. So that's reference partitioning in a nutshell. And the question we had was, how do we load them up quickly? And so because I got my question in advance, I can do a little bit of a demo of this one. Whoops, you can't see what I'm showing, so let me share my screen. Let's try that again. So here I have a table called par for parent. It's got an ID, a description, and I'm partitioning it into monthly chunks based on the created date column. And I'm starting at 2015. So that's just a normal partition table. I'm using interval partitions here such that the database will automatically create partitions for me, as opposed to me having to create them in advance. I'm going to create a child table as well. And this is the conventional means via which we create reference partitions. So the child table has a primary key. The parent has a primary key. So there's the parent primary key, which lets me now create a foreign key constraint on the child table referencing that parent table. And as a result, I can now partition by reference. So let's now see how it goes in terms of populating these tables. So first I'm going to insert I'm inserting about 5 million rows into my parent table. And here's the challenge. The parent table has a primary key index on it already, such that I could create the child reference partition table. So inserting those rows is going to be quite costly because it takes a while not just to insert the row data, but also to keep the table data updated as well. It took about 25 seconds. Now I'm doing the same thing on my child table, and it's going to have the same effectively impact. I've got a primary key index on the child, and I've got a foreign key constraint referring back to the parent table. So once again, even though I'm doing a direct mode insert using insert append, there's a high cost in actually doing this insert. And once again, it's taking, what have we got here? I pulled out a laptop. I can hear the fan going on it. It's belting away, and it's got, come on, laptop. It took 35 seconds. So the question was, how can we improve on that? I have to define all those constraints for reference partitioning. How can I avoid it? So I thought I'd give you a few clues. Here's the first option. One is I can create my parent table with no primary key. So now I can just insert into there, and there's no indexes or anything on this primary key. What I'm doing is deferring the creation of my child table until I've populated the primary key, the parent table first. So inserting into a parent table with no indexes, you can see is a lot faster, and then I can add the index as a secondary step. That took about 17 seconds, which is still a fair bit faster than the initial load. Adding an index after load is generally going to be faster. My child table, I can defer the primary key, but obviously I can't defer the foreign key. I can't not create that because otherwise I won't be able to do partition by reference. So I can try to populate that. I've got some benefit here because I haven't put the primary key on yet for the child table, but I still have to have that foreign key relationship in order to have reference partitioning. But so I've managed to remove one overhead, and so we'll see how it goes in terms of inserting the 5 million rows. And that was down from 35 seconds to about 22 seconds, and then add the primary key. So I've gained some time there as well. So that's another way, and this is a sort of a generic way we use with any kind of data loads, is try to defer any kind of index maintenance you have until after the fact. So even with reference partition tables, you can do that with the various indexes that aren't associated with the particular foreign key constraint. You can actually go probably even one step better. So this is probably where I would start for the person that asked that question. I would probably start at that level, try to defer the primary keys, load it like that, and see if that's good enough. To go to the next level up, you actually might have to go a little bit more complexity. So the parent table is being reloaded here in the same way as before. There's no indexes on it. And I'm going to insert the 5 million rows and then add the primary key as a secondary step. So that's no different to the previous demo we just ran. Simply load the rows, then add the primary key. Here's where things are a bit different. I'm going to create my child reference partition table, but rather than now go ahead and load the 5 million rows into it, what I'm going to do is I'm going to insert 1 row per partition. So I've only inserted 20 rows there, and then I rolled them back anyway. What that's going and doing is automatically creating the 20 interval partitions in my child table in preparation for load. So I've pre-created the partitions, but actually put no data into it. So that's step 1. Now I'm going to create a standalone table called child subset. It's a table which I'm going to load into chunks of data rather than loading my entire child table. So this looks a bit more complicated. What I'm going to do now is loop through each of my child table partitions, which is this query here. And then rather than load the child table directly, which has that immediate and always on foreign key constraint, I'm going to load it into my child subset table, which is a standalone table. Obviously, to do so, I need to know the exact definition and distribution of keys across the partitions, but this is, as again, generally used for a once-off load. So then what I can do is I'll load the child subset table, and now as an after effect, I can load that without having the foreign key on because it's not associated with the parent table yet. So now I'll add the foreign key, and then I'll exchange it into my child table. And that way I can bypass the validation of the foreign key. In fact, if I scroll across, we can actually see I'm choosing without validation. Obviously, I need to have some confidence here that data is loading, is valid. Then I'll drop the constraint, truncate the table, and loop around and do the next partition. So in this way, I'm actually loading the data, doing the validation, and then swapping it into the child table on a partition by partition basis. So we'll give that a run. And in this way, I haven't had to do a big insert of data into that child table with the foreign key enabled. So it's going to loop through each particular partition and chug away. I just realized the reason my laptop's running so slow is, of course, we're recording this meeting. But you can see there, we churned through it, we got through it in 17 seconds, and then we go add the primary key as a final step again. So that's just a little example of how you can speed up the loading of reference partitions. Just because you have to have the foreign key constraint, and just because the two tables are bound together, you can still take advantage of all those normal optimizations we have for loading large amounts of data in terms of deferring indexes as long as we can and deferring constraints as long as we can. Let's head back to our questions. Oops, wrong slideshow. How many partitions is too many? That's a good question. Here's my thoughts on it. Back in, I think, when we first introduced partitioning, up to our Oracle 9, I think the maximum number of partitions you could have on a table was about 64,000. It's obviously always a binary number because there's some integer somewhere floating around that controls the number of partitions. Now, I think in Oracle maybe 11, maybe 10 or 11, we bumped it up to, I think it's 1 million partitions per table. Now, the question is, should we be interested in going to that distance? I think what really matters is if you think about what dictionary maintenance has to occur to have a number of partitions, in fact, any number of partitions table, we can think about what the potential cost might be. So let's say I've got a table with 100 partitions and it's got 10 columns. Effectively, I've got the table itself and the 10 columns for that, and I've got 100 partitions, and those same 10 columns are obviously present in each of those 100 partitions. Now, when the optimizer is working with a database, it uses statistics, obviously, to work out the best way of actually running a query. So what we've now got is one of the things we store in the database is column level statistics. We store, by default, the high and low values for those columns. And so now I've got 100 sets of those statistics, one set of statistics for each particular partition. Now we can take that to the next level. In Oracle 10 and above, the database, unless explicitly told otherwise, will create histograms for columns if they're used in various predicates on queries. That's a whole new discussion. We can do that maybe in another DBA office hours. But so let's say I've got maybe 100 histogram values on each column on each partition. So now I've got 10,000 pieces of metadata on that one table to handle all the column level distribution of data. Now, when the query optimizer comes along to optimize a query, it may have to look at some or all of that information, or have to churn through a lot of it. Now, what that might mean is you might get the best optimization time for your best optimization for your query, but the time spent to optimize might get fairly large. And in fact, one of the risks with massive numbers of partitions is not really the maintenance of the partitions, is the parse time, the actual time to parse a query that references lots of those partitions might get quite long. Now, before I sound like that's like alarm bells or anything, generally, if you've got a large number of partitions, sometimes that means you've got a very large table and you're using it in, say, something like a data warehouse. Now, in a data warehouse, we generally expect queries to run for seconds, not sub-second, or maybe seconds or minutes. So spending that extra bit of time to parse a very complicated query, which has lots and lots of partitions, might actually be a good thing, because it might overall get a much lower response time for those very complicated queries. So I think the only risk point there is what I would call is dictionary pollution. If I've got thousands of tables, and each of those tables have thousands or tens of thousands of partitions, that's a very big data dictionary you're holding on to. You're going to gather stats on all the columns in all those partitions in all those tables. And then obviously in most versions of Oracle, we record historical statistics, such that if statistics make things go bad, you can restore stats that were, say, collected yesterday or the day before. So your sysorgs table space might get very, very large with all that statistical information. So I'm not saying don't do it. I'm saying be aware that if you do, there may be some mitigating circumstances you might want to consider. You might want to consider, for example, not taking statistics at the partition level. You might say, I'll only have the global level stats on that table for those particular tables that have tens of thousands of partitions. Now, having sort of maybe warned you off lots of partitions, let me give you an example of where I think you can have your cake and eat it as well. One of the things I really like about partitioning is the ability to actually use partitions a bit like indexes. So think about what an index really does. Index is about being able to access less data in order to satisfy the result of a query. Rather than scanning 10 gigabytes, I might only have to scan 100 megabytes using an index. Well, partitioning offers a very similar sort of use case scenario. If I've got a 10 gigabyte table split over 10 1 gig partitions, then certain queries that use the partitioning key as a predicate will be able to actually restrict the amount of data they scan. So take that to a logical next level. What if I took my 10 gigabyte table and broke it up into 1,000 partitions? Now every partition is only 100 megabytes. That can be scanned instantaneously almost on most modern systems. So very granular partitioning might be a really good performance benefit optimization for you. Now, how does that compare to what I just said about not having tens of thousands of partitions? Well, when I say have your cake and eat it as well, what you can do is, for example, let's say I've got a table which is accessed very aggressively for today's data. So what I might do is I might partition today's data by the hour. Now, when tomorrow comes along, tomorrow will be partitioned by the hour as well. But now that yesterday's data, or today's data has now become yesterday, or it's historical data, I might take those 24 partitions and merge them into a single partition using merge command. Now I've got one partition for yesterday and 24 partitions for today. At the end of the week, I might take those 7 daily partitions I've got now and merge them into a weekly partition. And then I might take those 4 weekly partitions, merge them into a monthly partition, and so forth. So for my aggressive queries I'm running today, I'm getting the benefit of very fine-grained partitions, hourly partitions, for example, yet I'm not creating this giant maintenance nightmare or dictionary nightmare with hourly partitions going back 24 years. I can take those very fine partitions and make them larger as the data ages. Now, you might be thinking, that's all well and good, but merge partitioning locks the partitions that are going to be merged, so I can't do any DML on those partitions, and that is true. But I don't think I'm giving away any secrets here because we've seen this in slides already. In 18C, which comes out pretty soon, my understanding is, we have a thing called merge online. So you can take an arbitrary number of partitions, not just 2. We can take, say, 7 or 8 partitions and merge them into one partition in an online operation. Now, you might be thinking DDL lock timeout does the same thing, but when you use DDL lock timeout, for those that are familiar with it, if I'm doing a big DDL operation, all the DML is going to queue up behind it, which obviously doesn't really work in an OLTP environment. So with merge partition online, you'll be able to do these big merge operations, hopefully in a quiet time, but you're not going to interrupt any OLTP operations. Any DML is going to stay nice and snappy. So look out for that when 18C comes out, because it makes that operation now of having a very customizable set of partitioning systems, big partitions for old data, small partitions for active data, etc., much more attractive. Okay, so hopefully that answers the question about how many partitions we should have. Man, the time is racing away. Can I set the name of my interval partitions? Yes, you can. Very easy to do. To set the name of interval partitions, all we have to do is we let the partitions be created, and so they'll get that that sort of system-generated name of sys underscore followed by some numeric number. But just like a table can be renamed, you can do alter table, modify partition, rename to something. I think that's the syntax. I think it's alter table t modify partition, rename x to y. Now, one of the challenges there is what are you going to name it to? Because generally, most people, when they're doing partitioning, use the partitioning definition as a way of naming it. So if they've got a partition which holds January's data, they want to name it, partition name underscore January, or something like a date stamp or something like that. So they want to have a nice meaningful name, such that the partition suggests what the partition holds. I've got a little video on that, which unfortunately I don't have the YouTube link handy, but I'll send it out. I'll tweet it out. Let me make a note. I'll tweet it out after the session. About how we can actually interrogate the high value column, which is in user tab partitions, and use it as a means of renaming our partitions. So yes, you can rename interval name partitions, and I'm a big fan of it because it just makes it much easier for the next DBA that comes along to actually understand what's going on in your systems. Okay, next question. What use are read-only partitions? Okay, so to set the tone there, read-only partitions came in it's 12.1 or 12.2, I can't remember, but 12C something. And that is you can take a particular partition and say alter table, modify partition number 1, read only. And if you're online, whoever asked that, if you could elaborate, that would be good. But I'm assuming that the question was asked in the sense that we've already got alter table read only, which obviously sets the entire table, but we've also got read only table spaces. And if you look in most documentation in the Oracle database, one of the means we said about having read-only partitions in the past was you would simply take that partition, move it into a table space, a dedicated table space, and set that table space to be read-only. So in that sense, we've already got the concept of read-only partitions. So I'm assuming here, yell out if it's not the case, that someone's saying, well, why would you bother having a command, alter table, set partition read-only? There's a subtle difference here. When you move something to a table space and make that table space read-only, you've physically made the data read-only. It cannot be touched by any way, shape, or form. It is literally locked. And we do that because you might want to make that table space a read-only file system, or even go on read-only media. You could sit on, say, a tape or a CD or something that gets exposed as a file system to the database, but it's inherently read-only. When you do alter table T, modify partition, make the partition read-only, and you've set a flag, what you're actually doing is setting a metadata flag in the dictionary saying you are not allowed to do DML on this table anymore, on that particular partition anymore. So you can't do delete, insert, update. You can, however, do maintenance. So I can say a partition is now read-only. You can't make any transactional changes to it. But even though it's read-only, I can do move partition, I can do compress partition, I can rebuild indexes on the partition. So all those maintenance activities that DBAs might like to do, especially as data gets older, and that's probably the prime reason why you might make it read-only, you can still do. You can compress it, you can shift it around to other table spaces. All the good maintenance are still available, safe in the knowledge that no one's going to be doing DML on it. So that's the subtle difference, and that's why I quite like the read-only attribute on a partition. It can be used obviously hand in hand with physical read-onliness on a table space, but this is a nice little enhancement. Okay, what do we got next? Async global index mate seems worse than before. Okay, we might need to do a little bit of review here and then come back to actually answering this question, because this is something I noticed as well. I saw someone talking about on the forum about this, about the new async global maintenance feature. So let's find out what that is first. So let me share my other. Okay. So we spoke about global index maintenance before, in that if I drop an old partition and choose the update indexes clause, then my index does stay available. But effectively what's going on behind the scenes is the database is going and physically deleting from that index all the row IDs, all the index entries that are applicable to that particular table partition. It's like a big giant delete, as if you did it yourself. That's obviously very expensive in terms of undo and obviously redo. It's a big operation. But yeah, the advantage of the index is always kept available. It doesn't get marked unusable. Now in 12C, we introduced this thing called asynchronous cleanup, which is designed to solve both those problems in a nutshell. What happens in async cleanup now is you drop a partition, even though you say update indexes, it returns immediately. It simply says, yep, I'm done, which sounds sort of counterintuitive because how did it go clean up all those index entries without marking and not set the index to unusable? And that's what we call asynchronous cleanup. We didn't actually go change the index entries. As I said before, right at the start of this session, which is obviously a bit of a memory test for you guys, I said a global index has an extended row ID. It knows which particular partition that we have to actually map the index to. So when I go look at a particular index key, not only do I have the row, I need to know the actual object in which that row is stored. Now, in doing so, when I do async cleanup, and this is conceptually, I don't know the actual physical implementation because I don't work in that area. What I'm effectively doing is saying, okay, I've dropped the sales partition for 2009. That might have object ID 123. I know that any index entry in my global index that has an object entry of 123 can no longer point to a valid object. So I can simply bypass that. If someone does a query, I know that that's actually no longer a valid index key. So I've left the entry there, but I know I can't actually use it. So in that way, the index is now still valid for use. I've just got effectively some garbage floating around inside it. That's where the async cleanup comes in. What the async cleanup does is says, okay, a nightly job, some task will come along and go looking for that garbage and clean it all up. Now, my guess is the question someone said is that async maintenance seems more expensive than the actual update indexes command we used to use before. And I did some testing on this. I haven't done a test case for it, but it was true. If I do drop, previous to 12, if I did drop partition update indexes, I might burn, say, a gigabyte of redo in all those deletes going on. I do it in 12.2. It's instantaneous, but the nightly job burned heaps more redo and was much more resource intensive. And so I reached out to the guys that look after partitioning about why this is the case, because isn't this just doing the same operations before, but just in a nice quiet time at night, so we can keep the system rolling through nice and available. It actually does more, and that's why it's actually a really cool option. Not only do we do that big delete that I spoke about before, we go delete all that garbage. Once that deletion has occurred, we actually also perform a coalesce style operation to actually make sure that any index and keys that have been left fragmented are actually cleaned up as well. So it's not just like a big delete, it's actually a big delete and an alter index coalesce style command to actually compact those index entries such that from now on, they'll be used nice and efficiently, so we don't get sparse blocks polluting our buffer cache. So that's the reason why, effectively, they run actually more expensively in 12.2, and I think there's even a patch that actually lets you choose as to how resource intensive you want to be. But by default, I think what happens is we actually do the deletion and we do a coalesce as well to actually make sure the actual cleanup occurs. Now, I think that's the end of the predefined questions. So we've got about 10 minutes left. So if anyone wants to fire in anything on the chat, they can fire away. If you haven't got any questions about partitioning, we'll wait 60 seconds for questions about partitioning, but if you haven't, we can use the rest of this 10 minutes firing any questions you like, I don't mind. Someone's already said if we could do it, elaborate about exchange partition. Yeah, sure, I can do that. Let's see if I can find a slide on that. So we spoke about global indexes at length in this session. So a local index, as we said, is an individual index stored against each of the partitions. Now, they are obviously smaller chunks because I don't need to reference multiple objects. Each index only needs to refer to index entries in its particular partition, so it doesn't need that extended row ID. The nice thing with local indexes is if I drop the partition, then obviously only that index partition gets dropped. So I don't have to do any index maintenance. That effectively the partitions between the table and the indexes are bound together. I'll skip through this because we want to get to exchange partition. So here's a little demo. We drop the partition, and as you can see, all the indexes remain usable. I said that's awesome for handling old data because I can, for example, take an old partition and I can compress it to make it really small, or I could, for example, I could move that to crappy old disk and set that to read-only, as we spoke about before. We've got some stuff about RMAN backups, which we won't cover. Deferred segments, we won't talk about that. Let's get on to Exchange. Let's get on to Exchange. Let's get on to Exchange. Okay, yeah, handling new data. We'll go back one slide. One of the good things about Exchange partition, and we alluded to this in our reference partitioning demo, is we can prepare data that needs to be inserted into a large table that is exposed to everyone in a nice sort of insulated and controlled manner. So I've got 3 partitions there, 2010, 11, and 12. Let's say I've got 2013 to load into my system. Rather than just load straight into my new table, which might lock it, might take a lot of expensive time in terms of index maintenance, etc., all of which might hurt people running queries against that table. Or even if I'm doing piecemeal updates or piecemeal inserts, which means the data might get exposed before I'd like it to be exposed. What I can do is I can create a table totally isolated from that table. So it's not partitioned, it's not part of my sales table. I can load that data up. I can create an index on that table. So it's like a standalone table, it has no relationship to my partition table, but I can do all the things I need to do totally invisible to anyone else. I can index it, partition it, sorry, not partition it, I can compress it, I can do data validation on it, and only when I'm exactly ready to actually say, yep, 2013, I've checked it all, it's ready to go, I can actually create an empty partition in my sales table, and I can do alter table sales, exchange the partition 2013, which is empty, with my new sales table. That operation there is instantaneous because I'm not actually shifting the data. All I'm doing is telling the data dictionary that the table that was called new sales is actually now called partition sales 2013. And so now my sales table has 4 partitions in it, and no one ever saw that 2013 data until the very moment I actually did the exchange partition. It becomes instantaneously available with no overhead. So that's exchange partition. It's a really cool way of loading in new data into an existingly partitioned table. Okay, we have one last question, which I think we'll use before we wrap up, and that is, it's totally unrelated to partitioning, but we'll answer it, which is there any difference between sys and sysdba, or are both the same? So in terms of sys and sysdba, sysdba is a role and sys is a user. Now, we often use the term interchangeably, but a sysdba does not have to be a particular, anyone who is a sysdba does not have to have the username of sys. If I give the sysdba role to someone, which hopefully you'll never do, except for your genuine system administrators, it's not a role you would ever give out just like willy-nilly. Very few people should have sysdba, and as a DBA, you'll probably have sysdba privileges, but you should almost never ever use it. So if you're doing DBA activities, connect as a user with DBA privileges, not with sysdba privileges. Keep those separate. Only ever use sysdba for those things that must absolutely be done as a sysdba role. Startup, shutdown, database upgrades, patching, etc. Those kind of things. Right? Keep sysdba as this very preserved, locked away account. Super important. Sys is a user that has the sysdba privilege. Now, other users can have the sysdba privilege, and the reason people often get confused between the two is if you connect as, say, Connor as sysdba, the username that'll show me as connected as is sys. So everyone gets mapped to sys, but that doesn't mean they are one and the same. So hopefully that answers the question. So we've just got a few minutes left. If no one's got any other questions, none are coming in, which is fine. I'll just jump back to our questions and go to our concluding slide. So as I said before, please reach out to me. You can get to me on my blog, or I have a YouTube channel which I try to put videos on. I'll tweet out the how to use the Hive video. It's gone backwards. Let's turn off any delays. There we go, that's better. And please follow me on Twitter. For those of you that don't live in the US, where Twitter is king, I'd encourage you to get onto Twitter and follow me and other people who are Oracle technologists. Often, in particular, other people inside the Oracle organization announce key releases, key features, etc. via Twitter first. So it's a great way of staying informed and up to date as to what's going on. Saves you having to have RSS feeds on millions of blogs and stuff like that. So if there's no more questions, thanks very much for attending. If you probably in the next 20 minutes or so, if you go back to the same Ask Tom page that you were on for joining the session, there's a feedback facility if you registered. So feedback, please let us know, or reach out to me on Twitter. You can always, I'm always happy to take your feedback. If you have ideas for the next session, because this is a session really designed to be Q&A for you guys. All these questions came from the community. That's the way I like to run these sessions, such that it's things that we answer for you, as opposed to just sending content down the line. So thanks for attending, and I'll leave that slide up. And yeah, thanks very much for coming along, and we'll see you hopefully next month or at one of the other office hours. Thanks, everyone.